Good morning, guys. I'm going to get started. If there are a few latecomers, we will send the presentation round and upload this recording onto our YouTube channel. So yes, thank you very much for joining the second session of our series of three webinars under the GoodWe Pro Training Africa banner. Today's session is on load shedding, planning for it and what to expect. We find that through our service team, whenever there's load shedding, there is an increased number of calls and tickets that are created because of issues that are experienced under those specific conditions. We find that inverters will actually work well until it is asked to use battery power or there's load shedding, and then suddenly the system shuts off for either wiring issue, the battery's not being connected correctly, or the comms not being there, etc., etc. So the idea of the session with our team today is to give you guys the some insights into how the inverter works, the backup side, also covering the types of issues that you can expect to experience and how to solve them, and various other topics. Presenting today is my colleague, David Hovenga. You guys should know him by now. He's been with GoodWe for a while. And then my name is Andrew Tyler, on the sales and business development side for Sub-Saharan Africa. Just a reminder that we have another session coming up next week, Tuesday, which is the last of the three webinars, which is on the SEMS portal and tips and tricks on how to identify and find issues, etc., on your plant without the need to have to contact the service team. So in other words, solving an issue being experienced without having to contact the service team for assistance. And also just a second reminder, for any questions and answers, please do use the Q&A box on the bottom of the screen. That is the best way to do it, because we can address the questions at the end of the session, which is what we're planning to do. So please put your questions there, and then we'll get David to address those at the end. Thank you, David, and enjoy.
Thank you very much, Andrew. Good morning, everyone. I'll just have my video on to say good morning. I'll be looking to my second screen on the side, so I'll be switching my camera off for the duration of the webinar. Thank you very much for joining, you guys. So yes, this is going to be a more active, going through all the different scenarios, things that could happen, and where and what to look for. So let's get started. So firstly, we're going to go through how does the backup of our inverters work, the effect of the batteries on the systems, the different load types. If my backup shut down, what now? And what could occur when the grid is lost. So how does my backup work? So GoodWe inverters, we have DC coupled hybrid inverters. So what this means is internally, the inverter has a DC couple. So the PV array and battery are internally connected to a DC bus. So this is the most efficient way of charging your batteries. So this is what makes our inverters much more efficient than some of the other inverters out there in the market. So because when we're charging the batteries from PV, your efficiency is very high. And this also gives us the ability to charge the batteries from the AC as well, because our DC bus then converts to AC, and then that can push back for us to charge the batteries. So as you'll see in this diagram, we've got our PV panels and our batteries all connected to the one common DC bus internally in the inverter. Then the inverter inverts that to AC based on the smart meter and all of that. Then we have our backup loads and our grid loads all in one device. Then just a brief touch on some other topologies. So like our AC retrofit inverters that we have as well, which we don't really sell in South Africa. And some other brand inverters also AC coupled. So which means the PV or PV inverter, separate PV inverter will be connected to the AC, and everything, all your generation, everything is first converted to AC. So your charging and discharging of your batteries, you do lose 1 to 3% of your efficiency just on that, because charging from the grid is a lot less inefficient than charging directly from a DC bus. Here's just a diagram of our systems. I'm sure all of you are quite familiar with this diagram. So internally in our inverter, we do have switching. So what our inverter does when you are connected to the grid, it essentially connects the grid and the backup together. So that's why it's essentially seen then as one load. So the inverter itself covers all load from the PV or batteries, especially if you're using general mode, which most customers use. It covers all the loads. But it is essential to swap, to split the loads in your distribution box. So we have to make sure that the loads on the backup output are the essential loads. So no large loads, no big motors, aircons, washing machines, things like that. If they work within your inverter specifications, because we now have like the 10 kilowatt EHBs, those ones can handle larger loads, such as your aircons and things like that. So normally in those cases, it's not too much of an issue. But when you are limited by the backup output, you have to make sure that your load is within range of your backup capacity, even when the grid is there. So here's just a brief overview of our hybrid devices and their capacities. So we do have different size inverters. Based on the size of inverter, there is a difference in the backup capacity. So our EM series only has one backup capacity, although there's different sizes of inverters. The EM is not very popular in South Africa because the backup capacity is quite low. So that's why it's generally not used too much in South Africa, because 2.3 kilowatt under backup doesn't allow for much. It's great for self-consumption systems with a small backup system for lights and TVs. But in most circumstances, customers generally want more on the backup, and that doesn't work very well. As you'll see, the peak backup on the EM series is 3.5 kilowatts for 10 seconds only. So it's very quick. ES, which is the device that's most in South Africa at the moment, which is a 3.6 and a 4.6 kilowatt. So we call it a 3.6 and a 5 kilowatt. So 5 kilowatt is the nominal AC output of the inverter to the AC grid. And in the backup capacities are 3.6 and 4.6 respectively. So the 3.6 can overload up to 5.5 kilowatts for 10 seconds, and the 4.6, 6.9 kilowatts for 10 seconds. So I'll go more into details how these overloads work now. So then we have the EA series, which isn't really in South Africa. Then our new EHB series, which a lot of stock will be arriving quite soon. So you guys can contact your distributors about that. So quite soon we'll have a lot of them in the country. So they start from a 5 kilowatt to 10 kilowatt. And you'll see the overload capacity on these devices is roughly 10 to 20%. So the 5 kilowatt can overload up to 6 kilowatt, and the 10 kilowatt goes up to 12 kilowatt on overload. But you'll see the overload time on these ones are quite a bit longer. So it's 60 seconds. Then we have the 3-phase ET. We generally only have the 10 kilowatt in South Africa. We do have smaller units, but that's way too small on the backup side for South Africa, because the 10 kilowatt gives us 3.3 kilowatts per phase. So that's it. The inverter can do a total overload of 16.5 kilowatts for 60 seconds, and that's 6 kilowatts on a single phase as a total as well. So if we exceed 6 kilowatts on one phase, the inverter overloads. If we exceed 16.5 in total for the 3 phases, it will also overload. So below you'll see the graph here is just an example. So all of our inverters work this way. So the 10 seconds for the EM and the ES, all sort of rough guidelines. So the 10 seconds is for almost the peak power of the inverter. As you'll see, here's an example of the ES overload. So with newer firmware and updates to our devices, you'll see how this 60 seconds works with our newer devices. So the ES has adapted that as well. As you'll see, the overloads based on the overloads. So the bottom line is our kilowatt capacity. So 4.7 kilowatt, 4.8 kilowatt, 4.9 kilowatt. And you'll see the overload times. So this is just a rough estimate. It's not a 100% accurate, yeah. So it's just a rough estimate that I did for you guys. So at 4.7, so just over 4.6, the inverter should roughly run for about 5 minutes on that 4.7 kilowatts. So it won't shut down immediately. But this is also based on having the latest firmware on your device. So if you have much older firmware, it could be more sensitive. So just keep an eye out for this. And based on the load, so as the load increases up until the maximum AC capacity of the inverter, then the overload time drastically decreases. So you see, we're at roughly just over 5 kilowatts, which should be around 1 minute. The inverter should be able to last before it overloads, and then that rapidly decreases. So as you'll see, then the 10 seconds does apply from quite close to that. But yeah, this line could most likely be a lot steeper than what I have indicated here. So this is with in mind that we do have sufficient power sources available. So your backup power is always limited, even if the grid is available. So with the grid, you should see an overload curve, something similar to this when the grid is available. But it's never recommended to install loads that do exceed this regularly. So in our inverters, we do have a changeover, which was depicted in the first diagram that we had there. So the changeover on our backup output is around about 10 milliseconds. So with a 10 milliseconds changeover, you shouldn't see lights flicker. You shouldn't even notice it because it is quite quick. As you'll see with our relays, as per regulations, there are double isolated relays. So it's always 2 dual relays, making sure the grid is double isolated. And you'll see this switching process occurs within 10 milliseconds. So as I mentioned previously, so you'll see when the grid is available, the relay is closed between the backup output and the grid output. So the grid and the backup are synchronized when the grid is available. But these relays will react also based on the inverter capacity. So the relays are a limiting factor. So some devices might have what they call a bypass relay that essentially eliminates a lot of this when the grid is available, so that you can draw a much higher capacity from your backup when the grid's available. Our inverters, unfortunately, do not have that. Also, personally, I don't like that type of topology because when you're running higher loads than your inverter capacity, you almost definitely going to have a problem when the grid fails, because those loads aren't going to go off when the grid's not available. So you can install a lot of extra equipment to make that happen. But with our devices, you don't require those larger loads to be on the backup output anyway. Now we're going to look at the effect of the batteries on our backup output. So what is very important when commissioning our inverter and setting the settings is the depths of discharge. So we have the on-grid depth of discharge and the off-grid depth of discharge. We have those 2 levels so that one can set a reserve for grid outages. So a lot of customers, if their primary goal is savings with a secondary goal of backup power, they normally set this identically as to, yeah, so if this was a Pylon battery or something like that, that's allowed to go down to 90% depth of discharge. You'll see 90% is using 90% of our battery. So that's the full use of our battery capacity. Should we set 10% there, it will only use 10% of the battery. Another thing to keep in mind is that the depth of discharge on-grid and off-grid are two independent settings. So should we want a reserve, we can leave our off-grid depth of discharge on the maximum like this. It's always recommended to leave it on the maximum. And then you just change your on-grid depth of discharge. So if you want to save 10%, we'll set that then to 80%. So it means for self-consumption and energy savings, we're going to use 80% of our battery, and we'll have that 10% of the battery just in case there's an outage. And we can also change this then if we know load shedding is coming, we can perhaps put that up to 50% on grid to have a larger capacity saved for backup. So having the correct size battery is required for stable operation. So very often there is constraints. It's normally financially constraints for our customers because I mean batteries are expensive. So we always have to fit within budget for the customers. So very often we have to install smaller battery banks to fit into the budget of these systems. Just one tip here before I go on to the next slide. Changeovers are always good to have included for customers for ease of maintenance and all that. Like our EHB series already has that included. So it's already installed on the inverter. No need to install an external one, but it's always good to have. So if there is any issues or too much load connected, or it's the middle of the night and the customer overloaded his inverter, or something went wrong with the batteries or inverter, they can just flip the changeover switch and continue on the grid. And you don't have to get up at 10 o'clock at night to get to your customer to make sure he has power in the morning. So yeah, there is a lot of data to look at. So this is just the graph to get the maximum battery power. So all of our inverters are, so the backup power is limited by your battery capacity. So let's look at the bottom at the ES, which is the most common and most familiar, which is a 48 volt system. So it's a nominal 48 volt and 100 amps. And that gives us our 4.6 capacity. So when we only have batteries available, our capacity is limited by our batteries and our charge and discharge capability of the inverter. So we'll see here 4.6 kilowatts. So when the grid is unavailable and all we have is batteries, we are going to be quite limited to that 4.6. For the devices, due to battery protection and not exceeding the battery discharge limits as well, the inverter overload time is a lot shorter, because it is reliant on one single source that doesn't have boundless energy. The overload time for just batteries on the ES series is about 2 seconds. So should they exceed the battery discharge limits for 2 seconds, it shuts down. So with the 48 volt system, it is quite simple. You just need your 100 amps for 4.6. So if you're using something like Pylon tech, that's 25 amp on a 2.5 kilowatt cell, or 37 amps on a 3.5 kilowatt cell. You have to make sure to have sufficient modules to get your 100 amp to have the full capacity. As you'll see, 75 amps gives you 3.6 and 50 amps gives you 2.3. So this is a good estimate to see what that amp rating will give you. So as I said previously, budget constraints are always an issue, but it's not a problem. If the customer can only afford a battery that's going to give us a 50 amp output, then we just need to make sure that the loads on the backup output are 2.3 kilowatts. That way, the system will work optimally, will work well, and the customer has room to expand his system and also add more loads to the backup output as he increases his battery bank. Then we move over to the high voltage. The high voltage are slightly more complicated because instead of current, because our current limit is fixed. So for the ET range, our 3-phase range, the current is always 25 amps, and all the batteries on the market do reach 25 amps. So Pylon, BYD, they all have a 25 amp limit or 50 amp limit. Pylon also has a 37 amp limit on the 3.5 kilowatt cell batteries. But with the the inverter itself is limited to 25 amps, but we have a voltage range of up to 600 volts on the ET. So for 5 kilowatts, 200 volts is sufficient. So if we have a 10 kilowatt ET and we can only put a battery bank, so 4 batteries of Pylon or 2 BYD HVSs, I believe, you should have around 200 volts. And that then your maximum load under backup should then only be 5 kilowatts. To get your full 10 kilowatts, we need at least 400 volts at the 25 amps. And it's always important to make sure that the lower end of your battery voltage is near this mark. Because if your battery when full is at 200 volts, it's going to most likely be 180 volts when it's low. So that will also then decrease your maximum load capacity as the battery discharges. Then with the new EHB series, we have a discharge limit of 50 amps. So should you use Pylon batteries, like I mentioned, the 2.5 cells generally give you a 25 amp maximum discharge. The 3.5s give you a 37 amp. So you just have to do that calculation of, you can take the maximum current divided by, or the inverter capacity divided by the maximum current that you have, and then it will give you the voltage you require to get that inverter's full capacity. So if you're using a battery that can give you 50 amps, like one of the models of BYD, you simply require 100 volts to get 5 kilowatts and 200 volts for 10 kilowatts. So with the EHB and the higher current capacity, your battery bank can be slightly smaller to still give you your full peak capacity. I'm not really going to go in about kilowatt hours for how long you're going to run your loads at 200 volts at 10 kilowatts. That will most likely not be a very long time, but for a minimum amount for a system, this is what you need to keep in consideration. So when using the compatible lithium batteries on the CEMS portal, it's always important to make sure you can do it via the PV Master app as well. In advanced settings, you can see the charge and discharge current limits, as well as the voltages. It's very important to note that all of these figures are dynamic. So with a high voltage battery, the high voltage battery doesn't set the voltage at the maximum allowable for the battery. It slowly ramps up the voltage as the battery gets full. Where a low voltage inverter normally keeps it at this steady, so 48 volt in this case, it keeps your charge voltage at a steady voltage. So it says you're 53.2, and that's the voltage it puts out, and then it just manages the current output. Where with the high voltage, it gives out a fixed current and the voltage increases as the battery charges up. So these figures are dynamic. So very often when you open that advanced settings in PV Master or look here on the CEMS portal, we see different values. So these values are from the battery BMS. So this is specifically an ES. As you can see, a 504 ES. Yeah, we're seeing only 74 amp discharge. So from my experience, I know this is 2 US 3000 batteries from Pylon on here. And that's limiting us at 74 amps. Should the customer actually have 3 or 4 batteries and we're only seeing 74 amps here, then we know there's a problem on the installation side and the batteries aren't communicating with one another. So that's why it's very important to check here when we're done with our installation. One of our checks that we need to do is make sure that the inverter is reading from the BMS correctly. So I have seen it personally myself, that customers will install 4 or 5 batteries, leave the site, and it's no problems because load shedding happens every 3 months. So the system runs for 3 months and load shedding happens in the inverter trips, and we come and look and we only see 1 battery here. So it's just one thing we have to keep in mind. Now I'm going on a bit about load types. So I'm sure most of you are very familiar with the different load types, our resistive loads, like our heating elements, toasters, ovens, all of those different devices. They consume power in such a manner that the current wave remains in phase with the voltage wave. So as you'll see, our graph on the side, our voltage and current are synchronized. So that gives a power factor, normally a unity power factor, a power factor of 1. So resistive loads are the nicest loads to run because they use a 1 power factor, so they don't cause any problem in our systems. The second, we have capacitive loads. So a capacitive load causes the current wave to lead the voltage wave, so that it has a leading power factor. So this is normally things that are, so cables have capacitive loads, also capacitors themselves. So in lots of equipment, DC chargers, your motor startups, all those kind of things, they all have capacitors as well. But capacitive loads normally don't really affect the system too much and are generally quite small in the long run compared to the loads that we are running. And then we get our third load type. And this load type is normally the problem child. So our inductive loads. So electrical motors are generally inductive loads. So fridges, fans, vacuum cleaners, dishwashers, washing machines, compressors, all of these things have motors in them, and all motors are inductive loads. And this load consumes only reactive power. So the voltage and current waveform are out of phase by 90 degrees. So that's why it consumes reactive power, because the voltage is leading the current. So it has to ramp up the voltage first, and then the current ramps up. So the power factor of these devices are always lagging. And most power factors on our grid is already lagging. So when these devices start up, it lags even further and causes a much higher current draw. So in this also, the power flows from source to load and from load to source. As the motor starts up, some power flows back into your source. So that's why inductive loads are quite a big problem in backup systems. They can also draw 3 to 12 times the rated current on startup based on the power factor of the load. So I have, in my experience, found this many times, that an inductive load causes a problem. So especially customers when they have smaller battery banks and things like that, even something like a washing machine that is rated without elements for 500 watts, because its motor is a 500 watt motor. And the power factor on the motor just caused the inverter to trip unless it had its full battery capacity. So it's very important to note about inductive loads. It's something that's always overlooked because it's generally not worried about when the grid is available, because the grid absorbs this. The load time is normally very short. It's normally 2, 3, or 4 seconds. Then that large spike is passed. So when we connect it to the grid, it's not a problem at all. But when we only have batteries available and our overload time is only 2 seconds, this large spike does cause an issue. You'll see, as for our ES inverter, we do have some stipulations regarding the load types. For inductive loads, you'll see we put a maximum rating of 1.5 kVA for a single inductive load and 2.5 kVA for total inductive load power. That total inductive load power is the peak power demand for an inductive load. So should your 1.5 kVA inductive load have a good power factor, a good capacitor, good motor starting, it can run on the backup of a 4.6 kilowatt inverter. It will run without any issues. Should we have our full 100 amp discharge available? But should that power factor of that device be poor, and that is drawing 6 times or 8 times or 12 times its rating, it will not work on the backup output of that inverter. So this also counts for booster pumps. So a lot of customers these days have water tanks and pressure booster pumps, and they're normally the cheap kind. And the cheap kind, unfortunately, does not have a good power factor. The capacitors are normally also too small actually to start up the motors properly. They have all different kinds of problems. They start a bit at full speed, ramp up against the high pressure, which causes a higher demand as well to start up. And all of these factors cause higher inrush currents and cause the device to trip as well. So it's very important to look out when designing systems to go look at what kind of inductive loads these customers have. If they've got booster pumps, if they've got things like that that they need to run on backup, it's important to make sure that the system is sized correctly for that type of load. One could also use a meter that has a very high resolution to measure the startup current draw of that motor. That is the best way of doing it, to see, and then you can recommend to the customer that either he needs to install a better motor or have some sort of startup aid for his motor to make sure that it does not give that peak current draw. And now we move on to my backup shutdown. So when our backup shuts down, normally the first thing that we do is phone the support center. And unfortunately, when load shedding hits, our support center is also hit with a large volume of calls and support tickets. I'm sure a lot of you are familiar with our support ticketing system. I've not added it here, because we've had that in previous trainings as well, which you can go view on YouTube. But yeah, when load shedding happens, we have a large volume of incoming calls, and everyone needs to know why their devices are shut down. But our devices do have mechanisms for you guys to view to see exactly why it shut down. So as you see here, the troubleshooting steps, I'll go more into detail into this, but this is something that actually needs to be done on installation, is to confirm that your peak load demand on the backup output is within range of the backup capacity or the battery capacity. We can view the maximum charge and discharge currents and SEMS to ensure the loads do not exceed this rated power. We can confirm that the SOC limit set has been reached. So for us with installer accounts, you can just open your SEMS app, go to your customer's plant, and go and see what the SOC limit is set to see that we've reached our set SOC limit. We can also ensure that minimal inductive loads are connected to the backup, as I just mentioned, with the different loads. And of course, that we do have batteries and the batteries are on, and we can see the battery voltage. Sometimes batteries do have issues as well, and they can shut themselves down. And if the battery shuts off, we won't have backup. So one of the first places we can go and look to see what is happening is the SEMS portal. So next week, we'll go do a live intro through this. So on our SEMS portal with our devices, you'll see the device tab at the bottom. We have our different inverters. So if one specific inverter shut down, we can select which inverter. And then we can go into the curve data. Yeah, you'll see we get a drop-down list that you can scroll down to view the P backup. So in the P backup, we can come here and have a look and see what kind of loads are running on our backup output. So when the grid is available and we have that longer overload time, you can see we do very often see the loads from the grid. And as you can see, this one ran for a few periods and then the backup shut down completely. You see the dip down to 0. So this wasn't load shedding or anything like that. It's just the backup shut down because we exceeded the load capacity of a 4.6 kilowatt inverter for an extended period of time. And when the grid is unavailable, very often we can't see the exact load that occurred when the device shut down. So this device, the backup here, you can see there aren't a lot of loads connected to the backup of this device, but we can see there are high spikes. So these spikes are peaking up about 3.5 kilowatts, 3.8 kilowatts. Sometimes they go about above 2.4 kilowatts. So we can see there are loads that do spike on the backup output of this inverter. This inverter specifically only had a small battery bank, so only a 50 amp discharge. So it means we are limited to 2.3 kilowatts. So this is the most likely cause that a spike happened. So generally we can also view the grid. So if we go back to another slide like this, so if we're viewing the date and time, we can see when the grid shut down. So we normally can look here quickly and see, okay, the grid shut off at a certain point in time. We can look at the P backup and see, okay, the grid shut off at 7:30. So the inverter backup was running for a certain period of time, and then it shut down. So there are ways to see exactly what happened. The easiest way most customers find is to call out Support Center for them to go and have a look. But you guys can also have a look as well. Which I'll show to you shortly. So yes, one of the things we check here, so if the battery discharge limit is exceeded during load shedding, so if our settings aren't correct, if our current limit from the BMS is not correct, so also when the battery is flat, we'll also see the discharge current limit will also go lower. And as this picture here, you'll see this device did not restart itself after it tripped off. So this device is also on an older firmware. So on the newer firmware for the ESs, the 21 firmware, we have added an auto reboot on these systems. I'll go through that a bit in the next one. And as I said previously in the troubleshooting, ensure that the device has not reached the set off-grid SOC. So here's one of the places where you guys can go to see what fault happened. So unfortunately, the SEMS portal doesn't always get these errors and warning codes from the devices, but the device does store it. The device stores the last 100 alarms or warnings. So the simplest way to see what the reason was the device shut down is to go to PV Master. So this isn't locked behind the installer password. So if you have a customer that you do trust to have PV Master, you can ask them to open PV Master, connect it to their Wi-Fi. They can then go to the parameters tab, go to the alarm tab, and they can send you screenshots of the alarms. So here we can see internal fan failure 4096. That is overload. So that's overload of the backup output. Unfortunately, the code had overlapped with our grid tie inverters many years ago. For the grid tie inverters, it was an internal fan failure. For our hybrids, there isn't an internal fan to fail, so it's nothing to worry about. It is specifically a backup overload. So should you ever see this error, it means backup has overloaded. As you'll see, this one had it several times. So very often you'll see here, and you'll look at the timestamp when this thing shut down, and then we can look at the timestamp here to see if they match the shutdown or when the inverter came back on again. So very often the error might occur and the inverter will log that error, and then we can see it here on PV Master. And only if you do not find your faults or errors in any of these sections, then please do make a support ticket with our support team so that we can draw the data on the back end and have a look, because we can sometimes also see these errors. But it's always advisable, especially load shedding time. It gets so busy that we can't always get to everyone's calls in time or quickly enough. So that's why you guys can also help out by looking on the PV Master app. So then next is just a list of things which does, or in my experience, has occurred previously when we have outages. So very often it is installation related things that do occur, especially like I said earlier, you install the system and there's no load shedding for 3 months. So we see a working system, there's no issues. And 3 months later, we had installations for over 3 months happening. So hundreds of inverters being installed and never really stood the test of a load shedding happening. And then load shedding occurs and everything, all the new installations show all the teething problems. And that is most frequently what happens in our case, is that all the teething problems now come forward all at once because everyone has load shedding. So everyone who's had their systems installed for the last 3 months are all having problems. And then we get overwhelmed with support queries. So one of the most common thing to happen is that the batteries run flat, or the set off-grid SOC has been reached. Very often there is confusion with the set the off-grid SOC. Some people might set that to 10%, believing that it will use 90% of the battery, but that needs to be 90% to use 90% of the battery. So that's one of the #1 mistakes or errors people make. Unfortunately, we are all human. No one is perfect, and we all make mistakes at times. Then the second thing to happen is customer turns on loads, especially because it's been a few months now. The customer has no issues. It's becoming winter or colder. They plug a heater or something else into a backup plug. And now that load exceeds our rated battery discharge current or the inverter limit. So that's why we went to SEM's portal to inspect that P backup to see what kind of loads are running on the backup output. And we saw on that one that there's a lot of spikes happening, but the customer has a much smaller battery bank. So there is loads on there that should not be on that backup output up until the customer expands his battery bank. So if we can see that there are loads that regularly exceed the battery discharge limit, we can be fairly certain that that's the reason the inverter shut down. And then the third one is the backup does not come on after exceeding the discharge limits, which I did mention earlier. So very often customers want to manage their loads themselves, and they understand that their batteries limit their system, but yet they still demand that you put more on the backup output. So a lot of customers are more savvy with their energy usage and do manage this quite well, but they don't even know the grid has gone off. Then they go and boil the kettle and whoop, off goes the backup. So like for the ES inverters on the latest firmware, we have a restart function when it's only batteries available. Normally it will restart natively if there's more than one source. So if you have PV and batteries, it does automatically start back up again. So in the middle of the day, it's not a problem. The problem happens when it's at night. So 8 o'clock at night, I go to make myself a cup of coffee, my system trips, and now we'll have to wait until load shedding is over. But with the new firmware, it does resolve that, and the inverter does, after the overload timer, restart itself up again. But it is very important to educate the customers on this, that should they have turned the load on and the system trips, they must turn the loads off again. Because if the inverter tries to start up itself again and that load is still there, the inverter will trip off and then it will stay off, because it will see it as a serious error then, because it's a startup failure. So it's essentially a high current draw and startup. So as the inverter turns its output on, it draws the DC bus too quickly and the device shuts down. Then it will not restart itself, because it's seen it as a critical error. So it's very important for the customers to make sure that those loads are switched off. Then the inverter will restart itself. So that restart time is normally around 5 minutes. So should they see, oops, I put the kettle on, it tripped the device off, put the kettle off, and wait for the device to restart, and then it should be fine. But if they don't switch the load off and it trips and trips again and is now off on a serious error, then the only way to get it back on during that outage is with PV Master in advanced settings to re-enable the off-grid output. So something similar can happen in early mornings. This is a very rare occurrence that does happen. I think I've only had it twice in all the years, is that your battery runs flat during the night. So if a transformer is blown and you're sitting without power for an extended period of time and your batteries run flat at night, this is also something that one can educate your customers on, that should this happen and they're sitting, they know there's been no power, they have a small battery capacity and it shuts off, they should just go and switch the breaker to the backup output off. Because the problem is that when the PV starts up, the inverter will start up and give output. And normally early in the morning, there is 50 to 100 watts from our PV. And should our loads exceed that, which they most definitely will, even if a few lights are on, then the inverter will trip off again. And when it trips off, as I said, that serious error of shutting down on startup, then it will remain off. Then the customer will have to go and re-enable the off-grid output. So if that happens, it's just a case of switching off all the loads and re-enabling the off-grid output switch. And then the customers need to allow the batteries to charge. So once the sun is a little bit higher, they've charged their batteries a little bit, then they can put on the backup loads and continue as normal so that their batteries can charge as well as run the loads in the home. Otherwise, the batteries will just run flat again and the system will shut down. Same for when we have bad weather. If the customer's batteries are running very low and the weather is bad, there's next to no PV, the loads are exceeding the PV capacity, either they need to reduce their loads or eventually switch off the loads so that the batteries can get a bit of energy. Then there's just a last few things. And as I said, we're all human. A lot of times we send electricians to site to do work and just wire up these systems, and sometimes mistakes are made. So very often there are wiring issues, especially wiring of changeovers. Changeovers very often are wired incorrectly, and that results in sort of bypassing the backup constantly, or either putting the grid input into the backup when the changeover is flipped. So these are things to just be careful of, to make sure that the wiring is correct as per the user manual for our country, especially on the three-phase devices. There's a few things that one needs to pay attention to. So it's always important to reference the wiring diagram of the manuals when we're doing this installation. And then also smart meters. It's very important that the smart meter must be powered by the grid. The smart meter should go off when the grid goes off. Sometimes the smart meters are powered by the backup output. Then the inverter thinks that the grid is there, but the grid is not there. So sometimes that can cause a delay in changeover. So it's very important that the smart meter goes off along with the grid, so it doesn't send conflicting information to the inverter. And for the accuracy of your metering as well, it's always advisable to have your CT connection point and the voltage reading to the meter as close together as possible. Very often there is also floating current. So that's floating current between your neutral and earth. So sometimes, like on the ES, the backup earth terminal is not connected or anything like that. And then we can get that floating current. And that can cause issues with BMSs and such. If the BMSs aren't correctly grounded or poorly grounded, we could get strange occurrences happening. So it's very important to make sure that everything is grounded correctly as per the user manual. And if your batteries require grounding on them as well, please make sure that that is well grounded. But yeah, refer to your battery manual for that as well. And then Bms faults. So lithium batteries, unfortunately, are smart batteries as well. And they also sometimes have faults. Very often either the BMS has an issue, or there's something between one of the batteries causing a problem. And that can also cause the batteries themselves to shut their output off or limit their output or have a communication failure. And this very often can result in the backup not working. Especially on the high voltage. High voltage is fully reliant on communication. With a high voltage battery, if the battery doesn't communicate with the inverter, the battery shuts off. If the inverter can't communicate with the battery, the inverter will also not discharge from the battery. So it's very important to make sure that those devices communicate correctly and that the batteries are installed as per the battery manual. So you must not miss any ground cables or anything like that. If the battery requires it, we need to make sure that everything is well equally potentially bonded on our grounding. And that is all from my side. So now we can go through any questions you guys have. I can go back in slides if there's anything you want clarification on, or if there's any more information you guys would like to know.
Thanks very much, David. It looks like we haven't had any questions in the Q&A box during the session, but we'll give a minute or two for anyone who might have come up with something since you asked.
Yeah,
I guess sometimes
be thorough.
That's what I was going to say. I guess we can take that as a positive. People are starting to understand the products well, and of course you covered everything that was needed. So we'll just give it another minute. Otherwise we'll close off the session. We
So
got one question.
How do VSDs used to regulate motor speed affect inverter performance and durability? So VSDs normally, I mean, it is a capacitive load. Very often a VSD. It does use a capacitive load to distribute the motor power more evenly. So starting up a motor slowly and things like that normally does improve. So you don't have that peak demand. So very often customers install motor starters or VSDs to remove that inrush current, especially with pumps, because pumps starting up at a high head pressure normally do cause them to have an even higher inductive draw, because starting up against a higher head pressure takes a lot more energy to get that device running. And because it's trying to run at full speed immediately, you have a very high inrush current. So starting it up slowly, getting it up to speed normally eliminates that quite a bit. Yes, our presentations will be emailed along with the link to the video within a short time. So it will probably be within a week or so. We should send out everything to you guys.
Yeah, just to add in there, David, Sham, we normally send the presentations in one group at the end of all 3 sessions. So it will most likely be the end of next week. However, if there is something that you need urgently, then please reach out to David or myself via email. You know, maybe you want to show a customer something that you've seen in a presentation. We can then quickly pop it through to you. Otherwise, it does normally go out as a bulk email. That way, it saves you guys from receiving multiple emails.
So we have a question: why don't GoodWe make inverters fully parallelable on off-grid? So unfortunately, most of our devices, the design has not had that in mind. So to have it fully parallelable, the backup output, one needs to have a bit more hardware internally. So it is something we're looking on. So just for your information, that we will have sometime next year a generation 2 of our ES inverters, and those should have that parallel capability in them. But our product was not designed originally for that. So the main design for our products is to save as much energy as possible, as well as having backup capabilities. So where a lot of the African markets is purely focused on backup. So a lot of the products that do the full paralleling has purely backup in mind. And yeah, so it's something that we will definitely have in future, but it's unfortunate that we don't have it yet.
Yeah, there was just one comment from Rieta Stevens just saying, thanks very much, David. That was great. So that's always positive. If there are no more questions, I think it's 10 o'clock, so it's exactly an hour. So I think we can close off. Is that cool with you, David?
Yeah, all good.
Awesome. Yeah, guys, thank you very much for joining. I see we have a few people still left. I think some have jumped off just after the Q&A. But yeah, thank you very much for your time. We really do value you guys who constantly support GoodWe and what we have to offer. Again, I'll ask for you guys to speak to us if you have any opinions or ideas for upcoming webinars. The idea is to not sit and tell you how great GoodWe is every day. I think everyone knows that. The main purpose is to address any questions. That way we help you guys focus on topics that actually matter, instead of doing just generic topics every month or so. Just a reminder again, we've got one more session next Tuesday, which is on the SEMS portal. So I look forward to you guys joining that. Please do sign up. The link is shared on our LinkedIn page again. Otherwise, please do reach out for it. But yes, thank you very much, guys, and we hope to see you next week. Thanks, David, and have a lovely afternoon further, or morning, should I say. Thank you.
Thank you very much, everyone. Goodbye.